Welcome. This is Geometry A, Unit 8, Lesson 8. This is the Unit 8 portfolio assignment. It has really two parts. One part where we prove something, a partial proof at least, of the, well, it's a problem that's similar to the mid-segment theorem, but not exactly. It has to do with dividing two sides of a triangle proportionately. So I'll go ahead and do the proof. Your task is to turn it into a paragraph proof. Okay? So on a blank sheet of paper, sketch GHI. Triangle GHI. So I'm going to sketch a triangle, and this is any triangle. Sketch a triangle GHI. And your proof needs to include a sketch. So do include a sketch of the triangle GHI. GHI, GHI. Okay, G H I. And then sketch JK parallel to GH. JK parallel to GH. So we're going to be parallel to GH. And we're going to sketch JK, where J is on segment GI. And K is on segment HI. All right, so we've drawn these so that they are parallel. So I'm going to include parallel arrows on there. And then B, prove using a two-column proof or a paragraph proof. You're going to write a paragraph proof. I'm going to write a two-column proof. That GJ, so GJ, that's this segment right here, is to JI, that's this segment right here, as HK is to KI. This is also a theorem known as the side splitter theorem. Okay? That is, if I write A, B, C, D, that C is to D as A is to B. That it divides the side proportionately. All right. So let's go ahead and start with statement. And rule. First statement, we're going to start with the given. HG is parallel to JK, or KJ. The reason we know those are parallel is that was given. And where we're going to end our proof, don't know the step number, but it's going to end with GJ is to JI as HK is to KI. I don't know the reason yet, but hopefully we will by the time we reach the end. Okay, let's go ahead and start filling in the steps. This will have to do with congruent or similar triangles. We've got a small triangle and a big triangle that we're going to prove similar. And just to give you an outline of the plan, they share an angle. Angle I is an angle in both of them. We're going to use the corresponding angle postulate to prove this angle is congruent to this angle. Okay? And then by angle, the small triangle is similar to the large triangle. And because they're similar, all angles are congruent and all sides are proportional. So I will be able then to write that the whole to the part is consistent. So GI is to JI as HI is to KI. And I think we'll be able to go from there. Okay, so that's kind of an outline of the plan. Step 2. Let's start with the angle. Angle I is congruent, angle I, not A. Angle I is congruent to angle I. Anything is congruent to itself is just a reflex. It's a knee-jerk reflex, like getting hit on the knee with a rubber mallet at the doctor's office. So it's the reflexive property of congruence. Okay, so let's go ahead and mark that. We've got an angle congruent to an angle. Okay, then I want to say angle J here is congruent to angle G, but I can't call it angle J and angle G. That's too ambiguous. So I need to label it angle KJI is congruent to angle, remember the vertex is always the middle letter, angle HGI. Step 3, that's by the corresponding angle postulate. Corresponding angle postulate. So we've got an angle congruent to an angle. Now angle is sufficient to prove the triangle is congruent, so 4 are similar. So triangle KJI, the small triangle, is similar to triangle HGI. And that's by the angle similarity postulate. Now if triangles are similar, their sides are proportional. So I can now write step 5. Okay, I'm going to go big to small. Actually, GJ is, yeah, let's go big to small. Yeah, big to small, just to be consistent. So GI is to, that's the big, that's this one right here, is to JI as, is to JI as HI is to KI. And that's because similar triangles have proportional sides, or I will cite the definition of similar triangles. Okay. What's more, step 6, GI can be written as GJ plus JI. The big segment is the sum of its small parts. GJ plus JI equals GI. Okay? And on the other side, HI equals HK plus KI. And the reason for that is segment addition. It's called the segment addition postulate. You can add two small segments to make a big segment. Now let's do a little substitution. Instead of GI, I'm going to write GJ plus JI. And instead of HI, I'm going to write HK plus KI. Substitution. So 7. GI is going to become GJ plus JI over JI equals, HI is now going to become HK plus KI divided by KI. Okay, 7, substitution. Eight. Let's break it up. You can distribute division just like you distribute multiplication. GJ is to over JI equals equals plus JI over JI. And HK over ki equals ki, not equals, plus ki over ki. Okay, so 8, that's the distributive property of division. So 9, Gj over Ji, anything divided by itself is 1, plus 1, equals Hk over Hk over Ki plus 1. Anything divided by itself is 1. Rather than cite the name of the rule, I'm just going to say anything divided by itself equals 1. And now we're ready for it. Subtract 1 from both sides, and we get Gj is to Ji as Hk is to Ki by the subtraction property. Of equality. Whew. All right, so that's the proof, and it only took a little over 10 minutes to do the proof. 10-step proof, fairly complicated, but your job is to turn that into a paragraph proof. All right, let's go on to the second part of the portfolio. Okay, on a coordinate plane, so on a coordinate plane, let's get rid of this and bring up a graph paper here. So on a coordinate plane, create triangle LMN. Now I'm going to create a triangle, but you create a different triangle following the same rules. So you're not allowed to use the same triangle I use. But on a coordinate system, on a graph paper, you're going to create a triangle in which there we go, in which we have triangle LMN where LN is a vertical line segment. So let's put LN right here. LN is a vertical line segment, and MN is a horizontal line segment. MN is a horizontal line segment. So we not necessarily, by those restrictions, have a right triangle. Okay, you're going to make your triangle different than mine, but you are going to make LN a vertical line and MN a horizontal line, and their shared point is N. So it's going to be a right triangle. Where you have the freedom to differ is where you put it on the graph, and the length of the length of the sides. Okay. Label the points. Okay, and all right. Then create segment QR, line QR parallel to LM such that point Q is on N, LN, and point R is on MN. So we want to create a line that's parallel. So it's going to be parallel. And I'm going to make it go right here. And right here. Okay. And where LN has point Q, and MN has point R. There we go. So these are drawn so that they are parallel. Okay, and you're asked to find the slope and use the distance formula as well, I believe. D is find the slope, and then use the distance formula to confirm the ratio of sides. We're confirming again the side splitter theorem. That is that LQ is to QN as MR is to RN. Okay, that divides the sides proportionately to each other. All right, so let's go ahead and do the coordinates. L here is 2 and 2, 4, 6, 8, 10, 11, 2, 11. N is 2, 3. M is 2, 4, 6, 7, 7, 3. And L, we already have L. Q is 2 and 2, 4, 6, 8, 2, 8. Now I purposely made it go through a grid point here for Q, but R is not on a nice place. So R seems to be 2, 4, 5, actually 5, I'm going to say 5.2. 5.2 and 3. Now that isn't a guess or an estimate, and there's going to be a little bit of fudge room on this problem because of that. If we get results that are close, we will count that as a confirmation. We're asked to find the slope to confirm that they are parallel. So L, the slope of LM, can be found by comparing the 2 points, 2, 11, to 7, 3. Change in X is from 2 to 7, that's up 5. And from 11 to 3, that is down 8. So the slope of LM is going to be negative 8 over 5. Double that, that's going to be negative 16 over 10, or negative 1.6. Okay. And the slope of QR. Okay. Let's see. Q is 2, 8. R is 5.23. From 2 to 5.2 is 3.2. And from 8 to 3 is down 5. So the slope of QR is negative 5 over 3.2. No nice way to do that, so I'm going to bring up my calculator. Not my calcusooner, but my calculator. Like calculator, dude. And we get negative 5 divided by 3.2, 1.5625. Negative 1.5625. Are those close? Certainly close enough for the guesswork that I've done in determining the exact coordinates of 5.2. So to the nearest tenth, they are equivalent. So we can safely say that LM is probably parallel to QR. Okay, let's go ahead and confirm the distance. The distance between L and M is, and we can take this from the slope, 5 squared plus 8 squared. Remember, negatives don't matter when we're calculating distance. We don't care what direction we ran, just how far. 5 squared is 25. 8 squared is 64. 25 and 64 is 80, 91, which is approximately, and I'm going to save that for the calculator here in a moment, LM, because I'm going to do both problems at the same time on the calculator. QR is the distance between 3.2 squared plus negative 5 squared, or 5 squared. Okay. And I'm just going to use the calculator to find that. All right, so let's go ahead and grab the calculator. I like to do as much at once on the calculator as I can here. Square root 91 is 9.54. 9.54 should be enough precision here. And square root 3.2 squared plus 5 squared is 5.94. Now, what are the results we should get? We should get the same ratio of sides, right? The same ratio of sides. So the ratio of LM to QR is, let's take these results straight off. I'm going to say this is L and this is Q, and I'm going to do L divide Q. 1.61, approximately 1.61. Okay, so the ratio is 1.61. That's the ratio of these two sides here. Okay, and yeah, use the slope formula. Okay, we use the slope formula, and then we use the distance formula. And let's check out the other ratios here. And I think I got a little bit off task here. Okay, MR is to RN as MR is 7 minus 5.2 is 1.8. Okay, and RN is 5.2 minus 2, which is 3.2. Okay, and that's MR to RN, and this is LQ to QN. LQ is 3, and QN is 2, 4, 5. So that's 0.6. Let's check this out. 0.6. And 1.8 to 3.2. Let's see if that's 0.6. .8 to 3.6. If I can type. 0.5. Now here we have a little bit of error here. 1.8 to 3.2. Make sure I did the arithmetic right. It's off by a tenth. But a tenth error is not unexpected. Let's make sure. So 7. Yeah, so that's 1.8, yeah. And, oh, not 3.2. Yeah, 1, 2, yeah, 3.2. 3.2. Yep, I did the arithmetic right. Okay, so we can say that they're proportionate about. So MR is to RN as LQ is to QN. Okay. LQ, QN, yep. We don't really need the distance formula for that. It's just a horizontal. And how does it help confirm the triangle proportionality theorem or the side splitter theorem? That is that a line parallel divides the sides proportionately. If I label these A, B, and C and D, A is to B as C is to D is what the side splitter theorem says, or the triangle proportionality theorem. All right, let's go ahead and see what else we've got going on. Converse of the triangle proportionality theorem. On a separate sheet of paper, sketch. And sketch G. All right. Prove the following using a two-column proof or a paragraph proof. All right. Hold on, I'm going to set this up. All right, so we've drawn triangle GHI, We're going to sketch JK through triangle GHI such that J is on GI and K is on HI, and it appears that JK divides GHI proportionately. That is, it splits the sides proportionately. So we're going to draw a line so that it divides the sides proportionately. I'm going to save myself a little bit of writing. I'm going to say that, well, no, I guess I won't. Let's put J on GI and K on HI. And what we're told, what we're given, statement, and rule. Step 1 is what we're given. We're going to be given that GJ is to JI, yep, as HK is to KI. And that's what we're given. We ended up with this on the other proof. We're proving the converse, basically. Statement 1, this is what we're given. Okay? And we want to end up with that they're parallel. So we want to end, let's make sure we have enough room, with GH parallel to JK. Okay, let's go ahead and see what we can do about proving it. Okay, so the first thing that comes to mind is kind of working the last proof that we did a little bit backwards. Okay, we'd like to prove that corresponding angles are congruent. I'd like to prove that angle K here is congruent to angle H here. Okay, and then we could use the converse of the corresponding corresponding angle postulate. And so that's kind of where I'd like to go here. So I'd like to end up with angle H congruent to angle JKI. And I'd like to use, once I have that, as this last reason or rule is the converse of the corresponding angle postulate. Converse of the corresponding angle postulate. So the question is, how do I get those two angles to be congruent? And one is to prove that the triangles are similar. Because if triangles are similar, corresponding angles are congruent. So there we go. So notice what I'm doing here. I'm working a little backwards as well as working forwards. I know the starting point and I know the destination. So let's go prove the triangles are similar. So I know that angle I here is shared between the two triangles. Angle I is congruent to angle I, and that is by the reflexive property of congruence. Okay, we know that, let's see, we know that GI is to GJ. So let's do this. Let's kind of work the way we did the last one backwards. GI is to JI plus 1 equals HK over KI plus 1. We can add the same thing to both sides of the equation here. So addition property of equality. And now get a common denominator for GI over JI is, and 1 is JI plus over JI. Anything over itself is 1. HK over ki plus ki over ki. And 4, that is the identity property, we're going to call it. Anything divided by itself is 1. Okay, 5, fraction addition, common denominator, gi plus ji over ji equals hk plus ki over ki. Okay, fraction addition. Fraction addition has to have a common denominator. Fraction addition. All right. So now segment addition, gi plus ji. Oh, I messed up. gj. I'm misreading my own writing. gj. So gj plus ji happens to be gi, right? So step 6. gi equals gj plus ji, and hi equals hk plus ki, and that's segment addition. Okay, and now a little substitution. gj plus ji is gi over ji. Okay, hk plus ki, hk plus ki is hi, so equals, not plus, equals, okay, hi over ki. And that says the big is to the small as the big is to the small. So that's our two sides. So that is substitution. Okay, so 8, triangle GHI is similar to triangle JKI by the side angle, not side angle side, yes, side angle side similarity postulate. Now that I've got similar triangles, I can jump to it. I can bring up my last steps. Angle H is congruent to angle JKI because they're corresponding angles of similar triangles. So 9, that's the definition of similar triangles, that the sides are proportional. Actually, yeah, that the angles are congruent. So GH is parallel to GJ, 10, by the converse of the corresponding angle postulate. Whew. All right, so turn that into a paragraph proof. And let's make sure, is that the last of the portfolio? Okay, nope, there is one more problem here. On a coordinate plane, so again on a coordinate plane, let me pause while I set this up. All right, so on a coordinate plane, graph paper, create triangle LMN, where LM is a vertical line segment whose length is a multiple of 3. And MN is a horizontal segment whose length is a multiple of 6. So we want the vertical to be a multiple of 3 and the horizontal to be a multiple of 6. Okay, so let's go ahead and do the same corner point here I did for before. N, multiple of 3. So 3, 6, let's go 9. So LMN, where LM is a vertical line segment. And okay, LM, so that needs to be M. My cat wants attention. Okay. I hope he's not bringing in a critter. He does that sometimes. LM is a vertical line segment whose length is a multiple of 3. And this one happens to be 9. And MN is a horizontal line segment whose length is a multiple of 6. So 2, 4, 6, 8, 10, I'm going to go 12. Okay, N. Okay, so there's my triangle, following the rules. Again, you use a different starting point and or different multiples of 3 and 6. There are plenty of multiples of 3 and 6. Okay, so here's my triangle. Okay. Plot point Q on LM such that LQ and QM is a ratio of 1 to 2. LQ and QM. So 1 to 2, so half. LQ to QM is 1 to 2. Oh, no, not half. LQ to QM is 1 to 2. So one part, we're going to divide it into 3 parts, and we're going to take one part here. So I believe that's right here. If I divide it evenly into 3 parts, Q would be the first one. So LQ is 1 part, Q to M is 2 parts. There we go. And similarly, plot point R on MN such that NR to RM. Okay, so that the ratio is, so I made this 12. So 12 divided by 3 is 4. So 2, 4, 2, 4. There we go. And so we're going to go R right here. Okay, so there's R. So we're dividing the sides. We're starting with proportionality. And we're going to verify, hopefully, that the lines are parallel. Okay. Use the distance formula. Label the points. Okay. Use the distance formula to show that LQ is to QM as NR is to RM. Okay. So LQ is, we don't even really need the distance formula. LQ is to QM as NR is to RM. Substitution, LQ is 3. QM is 6. NR is 4. RM is 8. And this is a ratio of 1 to 2. They both reduce to 1/2. So we have verified that the sides are split proportionally. Of course, we set them up to be so. Use the slope formula to prove that QR is parallel to LN. So the slope of QR. So let's write Q's coordinates are 2 and 2, 4, 6, 8, 9. 2 and 9. And R is 2, 4, 6, 8, 10, and 3. So my change in X is 2 to 10, which is up 8, and 9 to 3, which is down 6. So the slope of QR is negative 6 over 8. Reduced by 2, that's negative 3/4. Now for the slope of Ln. Slope of Ln. L is 2 and 2, 4, 6, 8, 10, 12. So 2 and 12. And N is 2, 4, 6, 8, 10, 12, 14, and 3. 14 and 3. Change in X. It's 2 to 14 is 12. 12 to 3 is down 9. So the slope of Ln is negative 9 over 12, which is negative 3 if I divide by 3 and 4. So they have the same slope, so I can conclude that QR is parallel to Ln. Okay. Let's see what else we've got to do. We've proved that the lines are parallel if we divide the sides proportionately. They proved the converse of the triangle proportionality theorem because we proved that if sides are proportional, then the lines are parallel. All right, that is the whole worksheet. Whew. What a slog. Make sure your triangles are different than mine, and make sure to turn the proofs into paragraph proofs.